Welcome to lecture 45, Phasors. And this is not Star Trek. Phasors, this is a legitimate electrical thing. Now before we get into the notes, you see this website right here. I don't know if you can see my mouse, so I'm going to go like this. You see that website there? Let's go there. I'm going to go there first. Okay, this website is cool. You see what this website's doing? And by the way, let me turn me off because I find myself very distracting. Boink. Okay, you see this website here? Got a sine wave, right? Oops, I'm clicking on the wrong window. Here we are. Come on, you. Okay, yeah, we got a sine wave here, right? So notice over here the circuit. It says there's an AC power source here, and there's just a resistor across it. And then, because it's an AC circuit, you get an AC voltage here. Notice the graph says volts, and it's versus time, but don't worry about that. So you can think of it as degrees. So right there's 360 degrees. There's another 360 degrees, and so on. So there it is. Nice sine wave we got there, huh? Now here's the cool thing. That's a resistor. What if we add a coil, an inductor? Boom! I just started an inductor. Notice we've got another wave now. Because, let's see, you might remember this. I'm going to bring myself right to the top of my... This is where the resistor peaks in voltage. Now remember, the resistors peak at the same time as the current. So you can use this as a sort of a proxy for current. So the current is peaking, and because this is an inductor, the voltage of the inductor is peaking first. Eli. Remember Eli? L stands for coil. Eli, E before I, voltage peaks before current. Voltage peaks before current in a coil. So this is where the current is, but it's also the voltage across the resistor because the resistor follows the current. So if you now think of the yellow wave as the voltage across the resistor and this orangish wave as the voltage across the coil, what's the voltage across the entire circuit? Well, you can add them up wave for wave, just like in the last homework set. Or you can use this website. See this V here? I'm going to boink. The blue is what you get when you add the two waves up. And if you want, you can even play like this and go, oh, yeah, that looks about right. So if you add every point you care to go, pardon me, I'm going to stop at a random, stop at a random spot. The blue is what you get when you add the orange and the yellow together. Now here's 0, right? So I'm adding, what is that, 150? And then this thing's at a coordinate of like, well, not negative 300, but so you end up here. So you add a positive 150 with a negative 290, and you get a negative, whatever. It's adding them up, point for point, just like you did for your homework. Aren't computers wonderful? They can just do that for you. It's like so cool. Now I'm going to turn off the total. Okay. What if, instead of a coil, so there's my resistor voltage. Again, that's in the same place as the current. That's the voltage across the resistor. Let's throw a capacitor in there. Boom. Now we get a capacitor. Now remember, I'm going to bring this up to here. Okay. Remember, this is where the current is. The current follows the resistor. So the current is here. And for a capacitor, the voltage peaks later. Remember ice, Eli the ice man, in a S, which is a C, which is a capacitor, it's I before E. So the current peaks before the voltage in a, or you might say the voltage lags the current is usually how you hear it. So anyway, the capacitor peaks later. So that's cool. It knows, and we can add the waves, right? So in this case, if you add the two waves, you point by point, you get the blue wave, which is pretty close to the yellow wave. But it's not the same, right? It depends on how high the capacitor is and how high the resistor is. In other words, how many ohms is your capacitor and how many ohms. They're telling us microfarads. It would have been nice if they told us ohms, but they didn't. Oh well. I have to make my own darn website, I guess. But now for the real cool thing. Let's have all three. Huh? See? Now you've got like the homework for real, where we're adding three waves together. Here's the voltage across the resistor. Here's the voltage across the coil. Here's the voltage across the capacitor. Add them up, please, and it adds them up point by point, and your homework should have looked a lot like what this blue wave looks here. It should have peaked a little bit higher than the resistor. It should have peaked a little bit in front of the resistor, and I'm pretty sure it did. So that's cool. So you might be saying, oh, why'd you make us do it by hand? We could have just we could have just used this website. But I've got an even bigger surprise for you. Turns out it's even easier than using the website. There's a nice method you can use, and it's called Phasors. What's Phasors? Well, let me draw this phasor diagram and click on the phasor. Boom, there's a phasor diagram. You see that yellow arrow? That's called a phasor. It's like a vector because it's an arrow, has a magnitude and direction. It's a vector, but it's a phasor. It's a phasor because it spins. What am I talking about? Watch this. Watch the dot on the wave. See? The dot's rising. As the arrow is spinning, the height of the arrow tip is generating that sine wave for you. So mathematically, you can just substitute the phasor for the wave. The phasor represents the wave. Because again, if you think of the phasor as spinning in a circle, that will generate the wave. In fact, if you want to see it a little better, I can do one of these deals where it will, see, isn't that cool? Oh, you gotta love these things. It will actually, draw the nice little, you can follow it. So the height of the arrow tip is generating the height of the wave all the way across there. Now, Eli, remember Eli? He was an Iceman, right? But no, Eli, voltage is first, right? So if you have a coil, boink, the way you represent a coil is by drawing its own phasor. So the orange phasor is for the coil. This will generate the voltage across the coil. And notice it's exactly 90 degrees in front of the resistor. And as they spin together. See, so when the resistor reaches its peak like that, you can see that over here, the resistor is at its peak. Well, the coil is at 0 volts. And they just keep a spinning all the way around, all the way around, all the way around. When the resistor is back to 0, which is kind of like its starting point, the coil is at its peak voltage. And so on, and so on, and so on, and so on. Ain't that nifty? Ain't that nifty? Now, here's a question for you. We saw before that you can add the waves point by point. Well, how would you add two vectors? We've done that, right? Added two vectors, we've done that. Well, click on the add button and just like you'd think. You have a little bit, you have an X component, you have a Y component, there it is. This blue thing is the total voltage across the circuit. Now, ain't that the slickest thing in the world? Ain't that the coolest thing since ice cream? So you can actually generate that answer wave by not adding the waves point by point, but by actually adding your vectors together. Now I'm going to turn that off, and I'm going to throw a capacitor in there on top of everything. And you can see that the capacitor, because it's ice, the capacitor comes 90 degrees after the resistor, or after the current. The resistor and the current are the same, or they're lined up. So the coil was 90 degrees in front, the capacitor is always 90 degrees down. So look at that. And then the idea is they're like glued popsicle sticks. They keep that sort of a, what do you call that, a configuration or whatever. They keep that as they spin, generating all three of the waves. And if you want to know the total, you can add the waves point by point, or you can add all three vectors. And if you do that, you'll get this vector here. And this vector, which is called the resultant, or in this case, it's called the impedance, is actually it's actually generating the voltage across the entire circuit. If you measure the voltage across all three elements at once, it's going to come out to that blue wave. So that blue vector generates the total voltage across the circuit. And so that's what I wanted to show you, is that instead of adding waves point by point, we're going to add phasors together. And that's how we'll get the total voltage across the circuit. Okay, turn that off somehow. Back to our notes. Here we go. Hopefully this is still working. Good. Time for some notes, folks. Gotta adjust myself here. All right. So I got some blue ink, right? Yeah. Let's do a greenish. I'm in a greenish moodish kind of ish. So lecture 45. It's saying superposition using phasors. So superposition, that was the word we used last time when we said we're adding the waves together, that they simply really do add up. Well, so do phasors. So you imagine a vector that rotates counterclockwise, and as it does so, the height of the arrow defines a nice sine wave, just like we just saw in that circuit. So I encourage you someday, type that in. It still works. And you can play with that and have a lot of fun. There's actually tutorials there and everything. But why do we use phasors? We use them because it's so much easier to add vectors than it is to do the homework like we did last time, where we were adding things one point at a time. So to demonstrate, here is the homework that you just had last night, that you, or recently, that you turned in last. This was your last homework. And we had, in this case, I think, let me use one of these things. This was the resistor, and it had a 4 ohm resistor, right? So notice the height of that wave is 1, 2, 3, 4 units. 4 ohm resistor. By the way, again, that's a proxy for the current. The current follows the resistor. And then we had Eli, the coil, peaks first. And the coil, notice the height of the coil wave only goes to 3, and that's because we got 3 ohms for the coil. Okay. And then we also had the ice, the capacitor, which peaks after. So here's the capacitor wave. It's only got a height of 1 because it's only 1 ohm. Okay, so again, these aren't resistances, they're reactances, but they're ohms. That's what's the same. They're all ohms. And so then we added up our waves point by point, which was admittedly a bit tedious. And what we ended up with for the total of the across the whole circuit was we ended up with this black wave here. And this black wave, like I say before, is called the impedance. And something tells me I want to use red ink for that because I use a red wave. That's called the impedance, the Z. So, how would we add those 3 vectors? Well, what you do is you draw them. So notice a couple of rules here. You always draw the resistor to the right, straight east, straight right. Notice I made the length of the arrow 4. You try to scale it, right? Vectors have magnitude and direction. I want the magnitude to be 4, which means the length of the arrow is 4, and I want it to point at 0 degrees. Due east, straight right, 0 degrees. Maybe I should write 0 degrees. The coil is a 3 ohm, which means the length is going to be 3. And remember that for Eli, the voltage is going to come before. So the voltage is going to be 90 degrees, exactly 90 degrees before. Now the way I remember that is coil has an L at the end. And so notice the configuration of these 2 vectors, right? Makes like an L. So the coil goes straight up. That might be one way to help you remember. The coil goes straight up. It's at 90 degrees. And because it's 3 ohms, I made the length of that arrow equal to 3. Meanwhile, the capacitor is 1 ohm. And remember, because of Iceman, the capacitor is actually not up but down. It's the opposite. The capacitor is always the opposite. So it's only 1 ohm, so the arrow is pretty short, but it goes straight down. So that's also supposed to be a 90-degree angle. Now let's go back to our old vector homework. Remember how we used to do the old vector homework? We'd say, okay, you want to add vectors? Think in terms of their x and y components. This coil component has an x component of 0 and a y component of 3. The capacitor has an x component of 0 and a y component of, remember, it's down, so -1. And then this resistor has an x component of 4 and a 0 y component, right? So those are that's the rectangular form of all of our vectors. Now when you add them up, and I'm going to use red to stand for my impedance vector, so Z is what you get when you add them all up. And if I add the x's, I get 0 plus 0 plus 4 is 4. And if I add the y's, I get 3 plus a -1 is 2 plus 0 is 2. My impedance vector is going to be 4, 2. It's going to have an x component of 4, which means it's going to come out this far. It's going to have a y component of 2, which is maybe about this high. And then you can say, okay, an x component of 4, maybe I'll put the 4 there, and a y component of 2, I'll put the 2 there. That's our impedance vector. This generates this red wave over here. Question for you. How long is this? Remember, we used to call that an R. How long is this? Can you say Pythag. Square root of the x component squared and the y component squared, right? So let me grab out my trusty electronic device. So if I take a 4 and I square it, and then I take a 2 and I square it, and then I add them up, and then I say equals, and then I take a square root and I say equals, and I hit the SD button, I get 4.47. And that, by the way, would be ohms. So the total impedance for this circuit, that's what we call the total resistance when it's AC. We don't say total resistance, we say total impedance. And you have to have a new word because remember, this is resistance, but this is reactance. And you add resistance and reactance, you get impedance. Okay, a lot of words flying around. But it's 4.47 ohms. And if you look at the height of this wave here, try to read this grid. Here's 4, here's 5. Yeah, it's just about 4.47 ohms. Ain't that something? What about this angle here? Remember how to get that angle? It was a shift tangent. Remember that stuff? Y component over x component. So if you do a shift tangent of 2 over 4, let's see now here, shift tangent of basically 0.5, right? Shift tangent of 0.5, I'm getting an angle of about maybe 26.6 degrees. Now if you try to read here, remember this is 45, this is 90, right? 0, 45 degrees, 90 degrees. So this is a little more than halfway from 90 to 45. So, you know, this is a width of 45 degrees, and so half of that's 20, you know. So yeah, that is just about a 26.6 degree lead. The circuit voltage leads current. Now, why am I saying it's leading the current? I'll give you 2 reasons. The first reason I say that it's leading the current is because, look, the current peaks with the resistor, remember? You can always look to the resistor to say where's the current peaking. And so since it's peaking first, it's in the lead, so to speak. Here's another way you know it's leading. See? The arrow's in front. The arrow is leading. Okay, that means the voltage is leading. Sometimes when you add these impedances together, you'll get something down here, and that's because it's lagging. But in this case, it's leading. So voltage is leading the current by 26.6 degrees. The total ohms is 4.47 ohms impedance. That's what you got by adding the waves by hand, and that's what we got in how many, like a minute or whatever, just by adding the vectors. Now, isn't that slick? So that is the main thing that we're focusing on today. And I think I just got 3 examples. Yep. 3 examples. Let's go through this 3 times, and hopefully this will all start to become natural to you. Example 1, Roger has a series RL. Oh, notice this is not RLC. It's just an R, and that's an L. He just has the 2 circuit elements. Okay. Series, they're all hitched up together. I'm only going to do series in this class. The resistance is 50 ohms, and the coil has a reactance of 30 ohms. Do you remember the difference between resistance and reactance, by the way? It's basically whether energy is actually dissipated or lost. A resistor gets hot, you're losing energy because it's hot. You know, hot leaks to the environment. The coil, theoretically, does not get hot. It's like a pure spring without friction. It would theoretically just, you don't lose any energy in the coil. You do lose energy in the resistor. That's why we have resistance baseboard heating, because resistors will get rid of the heat for you, but we don't have resistance coils, or I should say we don't have coil heating. Anywho, so that's why the difference. What's our mission here? Our mission, find the impedance and phase angle and say what the heck it means. Okay, so we're going to draw the resistor as a phasor going this way. The length of that is 50. So it has components, an x component of 50 and a y component of 0. I suppose you might want to put an R there. The coil, remember coil has an L, and an L looks like this, so the coil goes up. And you want to make it approximately to scale. So it's 30. X component of 0, Y component of 30, and that's the coil, X sub L. When you add those 2 things together, you're getting the total ohms across the entire circuit. And to add them together, you literally add those two vectors together. So remember, you add your x components together. 0 plus 50 is 50. And then you add your y components together. 30 plus 0 is 30. And so that, in some sense, is the answer. That's our impedance vector. It has an x component of 50 and a y component of 30. Of course, what is it? You have to do the old square root of x component squared plus y component squared. This will give you your actual ohms. You have to find the length of that arrow to get your ohms. Remember, we drew this a length of 50 because it was 50 ohms, and we drew this a length of 30 because it was 30 ohms. So the question is, how long is that? And that'll be ohms. So 50 squared plus 30 squared equals, take the square root of the answer, equals, hit the SD button, 58.3. Just about 58.3 ohms of total impedance. Phase angle, that's the thing we call theta. It's right there. Just like when we were playing with vectors, you just take the y component over the x component. Make sure it's always y component over x component, right? Because remember, that's the tangent, right? That's the tangent arrow. Goes that way, so it's always opposite over adjacent to do the tangent. So we're shift tangenting the opposite over adjacent, the 30 over the 50. Shift tangent. 30 over 50 is 3/5, which is 0.6. I can just enter a 0.6. I'm going to get a, well, if I round it to a nearest tenth, I'm going to get 31.0 degrees. Positive, leading. E leads I by 31 degrees. That's what that means. The circuit feels like a 58 ohm total pushback. Again, it's only 50 ohms of actual resistance, but because of the springy effect of the coil, it feels like you have to push against 58 ohms to get any current to go through that thing. So that's what the impedance means. That's what the phase angle means, I guess. Let's see. Example 2, Remy, series RC circuit. Okay, so starting from fresh, except this time it's not a coil, it's a capacitor. Resistance is 50 ohms. Okay, cool. Capacitor, X sub C, that should be a little c really, 20 ohms. Find the impedance and phase angle. What does this mean? Okay. Whoops, I guess I was going to draw XY axes, but I don't think I will. First, you draw the resistor to the right, 50 ohms. In fact, I'm going to do it this way. 50 ohms. The resistor has an X component of 50 and a Y component of 0. The capacitor, remember the coil went up, so the capacitor has to go down. So this is the capacitor. It has an X component of 0 and a Y component of down, negative 20 ohms. When you add these two up, you can kind of see the vector is going to have to be down here somewhere. That's going to be the impedance. It's going to have an X component of, you add the 50 and the 0 to get 50, and it's going to have a Y component of, you add the 0 and negative 20 to get negative 20. There's your impedance. That's a vector in rectangular form. That's your impedance. Now to get the actual ohms, you have to do this thing. 50 squared plus 20 squared. You may recall that when using the Pythag formula like this, I don't like to bother typing the negatives in. Why type in a negative? You're just going to square it. It's going to go positive, so just don't even bother. So 50 squared plus 20 squared equals, and take the square root of that answer, equals, hit the SD button, equals. We got something like, depending how you round, I think I'll go to 1 decimal place, 53.9 ohms. Total resistance. Phase angle. Shift tangent of y over x. It's always, this is the angle we're looking for, from the x-axis to the red. And it's always opposite over adjacent, right? That's the tangent. So you have to do opposite over adjacent, which means we have to do the y component over the x component, which means the negative 20 over 50. That negative is important because it's going to make our answer negative, actually. So we're just typing this all in. Getting a phase angle of negative 21.8 degrees. Okay, so this means that the total resistance, the total pushback, is almost 54 ohms. And by the way, that's an interesting thing. If this were a DC circuit with two resistors, if we had a 50 ohm resistor and a 20 ohm resistor, those would add to 70, right? If this were a DC circuit, they'd add to 70. But it's not a DC circuit, it's an AC circuit. And if AC, 50 plus 20 adds to 54. How do you like that? It's because you're adding vectors, you're not adding just numbers, you're adding vectors. Okay, and then again, the negative phase angle means that voltage trails the current. The voltage is down here. This is where the current is. The current is with the resistor. So remember, they spin this away, so you can see the voltage is coming after, right? Whenever you have a negative angle, the voltage trails the current. Oh, maybe you should try this one yourself. It's the only one we got left. It's the only one we got left. You should try it. You done? All right, let's get out a fresh color. RLC. Oh, we got the whole shebang going this time. So the resistor is always to the right. And the resistor is 50 ohms. So it's an X component of 50 and a Y component of 0. The coil, that's the L, that's straight up. It's a 30. So the coil is, well, an X component of 0, but a Y component of 30 because it's straight up. And then the capacitor is down. It's only 20, so try to draw it more or less to scale. But the capacitor has an X component of 0. It's all down. It's all negative 20 for a Y component. Cool. That's that. Now I do like to do my impedance in red. The impedance is what you get. That's supposed to be a Z. Let's try to make it look like a Z. The impedance is what you get when you add all three vectors together. And we saw earlier that the easiest way to add vectors is to add their X components and their Y components separately. So adding the X components, 0 plus 0 plus 50 is 50. Adding their Y components, 30 minus 20 is 10, plus nothing is still a 10. So the impedance vector is going to have a positive X of 50 and a positive Y of 10. So notice 50 is coming out at the same distance as the resistor here, and 10 is like not so far up really. So here's your impedance across the circuit. Okay, so again, it's 50, 10. Now what we really want is the ohmage, so you have to do the old 50 squared plus 10 squared trick. So let's see now, 50 squared plus 10 squared trick. My calculator says just about 51.0 ohms. Huh, that's interesting. So notice we're adding 50 plus 30 plus 20 and getting 51. Part of that is because the capacitor and the coil, they're partly canceling each other, right? Because this one has a 30 up, this one has a 20 down. There's a lot of just cancellation going on right there. So it doesn't end up adding all that much pushback to the circuit. Anyway, it's 51 ohms, and then you want your theta. Shift tangent. You take the Z component, you take its Y over its X, 10 over 50. Notice it's coming out positive. So shift tangent 0.5, right? No, not that. Shift tangent of 1/5. That's better. Just about 11.3 degrees positive. Voltage leads current. Again, it's leading because it's up here. We're rotating around this way, counterclockwise, and so the voltage is peaking before the current. Use the resistor as a proxy for current. Okay, that was cool. I think I got through that faster than I was thinking I would. Got to admit, it's a lot of fun playing with that website. You should try it, man. It's cool. It's awesome. It's wild. I'm going to end my streams, what I'm going to do.